This is the first video in a video series on Maxwell's equations and its different representations. We're going to start with Maxwell's equations in matter. I'm going to assume linear isotropic media. That's a specific relationship between D and E and B and H, where E and mu are constants. And from that, we'll arrive at the geometric algebra form for an R3 basis, where we have a E1, E2, E3, which are all Euclidean vectors, all squaring to +1. We'll see that the Maxwell's equations can be represented as a hybrid differential operator that includes space and time derivatives, a field which incorporates both electric and magnetic fields, we call this the Faraday, and a multivector current, charge density, current density hybrid that includes the charge density and the vector current density. I've been lazy with my arrows here, so this is intended to be an arrow. The specific form of the Faraday is electric field plus I times CB. It will then go into the geometric algebra, space-time algebra representation, where we take the Dirac basis, which has basis elements gamma 0, gamma 1, gamma 2, gamma 3, and in this basis, gamma 0 squares to +1, but gamma 1, gamma 2, gamma 3 all square to -1. We're not going to use the matrix, any of the possible matrix representations of these, but we will just assume that they obey those square value relationships mentioned, and we'll see that the form of Maxwell's equation, also singular as it was in the R3 geometric algebra case, has this form grad f equals j, where this is a non-arrow grad symbol that incorporates both the space and time derivative terms in a different way than this, subtly different, and also a 4-vector current density, which is a constant times this multivector current relationship. From there, we're going to derive two other representations. We'll derive the tensor relationships, and we will derive the differential forms relationship. I think for this video, we'll probably just get here to the Euclidean space basis geometric algebra representation. Let's start and see how far we get. I've written out Maxwell's equations in their in matter formulation, and what we're going to do is we're going to normalize this representation somewhat. So look, in particular, we have a spatial derivative operator that has dimensions 1 over length, and here we have a time derivative operator that has dimensions 1 over time. So this means that our fields must have different units. That's undesirable. We're also going to plug in our values for H and D in terms of B and E, and we are going to see how we can make this a little bit tidier to start with, even before we get to geometric algebra. So a reminder that we are going to substitute D equals epsilon E and B equals H, I guess it's H over mu, or H equals mu B. And we're also going to use the speed of light in the medium as the 1 over the square root of mu epsilon, and we're going to write eta as the square root of mu over epsilon. So with these transformations, let's tidy things up. So we're going to start here. Just going to move this sign over. So if to convert the 1 over time so that it has the same units as the gradient, we'll add in a 1 over c, and then we'll scale our field by pi c. So now we have dimensions of gradient equals dimensions of 1 over c d dt. So these dimensions equal 1 over length. And we have now dimensions of the electric field equals the dimensions of B times C. I don't really care exactly what units those are. We're working in SI units, but it's really not quite relevant at this stage. So we're going to scale all of our magnetic fields by C. And we need to substitute in H equals mu B. So right here, B mu mu. There we go. Now we want to scale this all by C. And D is E times epsilon. I'll just tidy this up. All right. Now, epsilon C mu is epsilon mu times C, which is epsilon mu times 1 over square root of epsilon mu, which is square root of epsilon mu, which is 1 over C. So, what do you know? Everything just happens to work out perfectly so that we get 1 over C d dt. d. And then down, oh, and there was a mistake here. That should have just been grad dot d equals rho. It's only now that we switch d equals E epsilon that we say rho over epsilon. So, and any other, so let's look at it. We have electric field, electric field, electric field. All the d's are gone. We have BC, BC, BC. All of our derivatives with respect to time are now 1 over c d dt here, and 1 over c d dt here. And we have all of our grad dots and grad crosses. So there's no geometric algebra here. This is just a way to put things in uniform units. And the only thing left to do here is let's look at C mu. So C mu is mu over the square root of mu epsilon, which is square root of mu over epsilon, which is our eta. So that's eta. All right. Here's Maxwell's equations, still in vector form, but ready to put into a simpler representation. I'm just going to regroup all of these. So we have grad cross E is minus 1 over C d dt of BC. Grad dot E is rho over epsilon. Grad cross BC is eta j plus 1 over C dE dt, and grad dot BC is 0. Having made this transformation, with this transformation, still just Maxwell's equations in vector form, but we can now bring geometric algebra into the mix. So what we're going to use is the fundamental identity of geometric algebra, which says that the product of two vectors is the dot product plus their wedge product. And in particular, we're going to write the dual form of the wedge product. So that is A dot B plus I times A cross B. And here I is E1, E2, E3, and we have I squared is minus 1. That I won't verify here today, but it's easy to do. So in particular, we can go and substitute A equals grad into this so that we have grad B, say, is grad dot B plus I grad cross B. And we see the perfect opportunity to apply that here in Maxwell's equations because we have grad dot E and a grad cross E, and we have a grad dot BC and we have a grad cross BC. So let us go and combine these pairwise equations into two gradient equations operating each on an electric or magnetic field. So the first one, for the electric field, we have grad E is grad dot E, which is rho over epsilon, plus I times minus 1 over C d BC dt. Now we have grad B C is eta j is I times eta j plus 1 over C dE dt. We're almost there. So the only thing that we have here that is a little bit non-uniform is we have grad E and we have a derivative of E on both sides, but here we have grad BC, and here on this side we have a I times BC. We can move the I into this term. Let's do that. So we have IBC in this equation, and here we don't have an IBC, so we can multiply through by I to get I squared on the right hand side, so that we have grad and I commute, because I commutes with any multivectors in R3. So we have grad IBC, and over here we have just minus 1. Now, let's rewrite this one more time, although we could skip steps, but let's not. All right. So here's the first stage of simplifying our Maxwell's equations. Not really, well, it's arguable whether it's simplifying, but it is at least merging Maxwell's equations. We've merged Maxwell's equations successfully into two equations, and we see that we have the same fields involved in both. And what we can actually just do is just add these two equations up. So we're left now with grad plus 1 over C dt times E plus I CB over epsilon minus eta j. So just to verify our terms here, we had a grad E, and we have grad ICB, so there's those two terms. And we have 1 over C ddt of ICB and 1 over C ddt of E. And lo and behold, we now have a multivector equation for Maxwell's equation in multivector form. We'll just tidy this up one last little bit by writing F equals E plus ICB, and we'll write J as rho over epsilon minus eta vector J. So in this electromagnetic field, what we're calling the Faraday, we have vector plus a trivector times a vector, which gives us a bivector. So this is a vector, bivector, multivector, and our charge and current density hybrid has got the charge density and the current density as a vector. And I wrote the arrow here, even though I've been lazy with arrows everywhere else, just to distinguish the two. So now that we have a multivector J, we distinguish it from our vector J. And if we do that, now our Maxwell's equation is the spatial derivatives plus the time derivatives of f equals J. One equation. There we go. Now, it's worthwhile to just reverse the logic here and make sure that we got everything correct. So let's go back and do that. And so if we go and verify, so if we want to verify that grad plus 1 over c ddt of E plus ICB is rho over epsilon minus eta J. All right, so let's expand out the left-hand side. So we have grad E plus grad ICB plus 1 over c ddt of E plus 1 over c ddt ICB. And we'll write this out in a little bit. So grad dot E plus grad wedge E plus I C grad dot B plus I C grad wedge B plus 1 over c ddt E, and finally plus 1 over c ddt of ICB. So we have here a scalar, bivector. Here we have a scalar times a trivector, so that is a trivector. This has grade 3. Here we have a bivector times a trivector, so that is actually a vector. So this one is grade 1, and finally we have a bivector, or we have a vector times the trivector, so that is a bivector, that is grade 2. So if we now go and group all of our terms, we should have one equation for every grade. So we write out our scalar term. We have grad dot E equals the scalar part of rho epsilon minus eta J, which is rho epsilon over epsilon. And any other scalar terms? No. So there's the grade 0. And grade 1, we have IC times grad wedge B. So that is I squared times C over times grad cross B. And we have plus 1 over C e dt. This equals minus eta j. Grade 2 terms, we have grad wedge e, which is I times grad cross e. Grade 3, grade 1, grade 2, plus 1 over c dt ICB equals 0. Finally, our grade 3 term is just IC grad dot b equals 0. So all we have to do is rescale these in some cases. So first case, we have grad dot e is rho over epsilon. That's just Gauss's law. And now here, I squared is minus 1. Let's just bring this to the other side as we normally do. So we'll have, and expand out that. So grad cross b is minus, so bringing dt here to the other side, we have a minus factor, but now we want another minus factor, so it's a plus. And we want 1 over c squared minus eta over c j. And in this equation, we will just cancel our i's. So we're left with grad cross SEE equals minus d dt b. And finally, canceling the IC, we have grad dot b equals 0. And just checking if I've got all my signs right, and do not. There should be a plus here. Let's see what went wrong. Oh, okay, because I divided by minus 1 and I didn't flip the sign. So that is plus. Now we have originally we had a term epsilon mu dE dt, but that is 1 over c squared dE dt. Okay, that checks out. And eta over c is the square root of mu epsilon times the square root of mu over epsilon, which is mu. All right, so this guy here is just mu j plus eta mu dE dt, which is correct. All right, there we go. So we've gone backwards and forwards from the vector form of Maxwell's equations to the geometric algebra form of Maxwell's equations, back to the vector form. All we had to do was apply grade selection operations to the entire multivector Maxwell's equation, and then we get out the 4 traditional vector forms of Maxwell's equations, at least for linear isotropic media.